Welcome to Presentation 8 of ENGG104, focusing on voltage division in series circuits. So far, you know about KVL, where the sum of the voltages across a series of resistors is equal to the source voltage. But what you don't know is how a resistor's value will affect the voltage across the resistor. It actually turns out that in a series resistive circuit, the larger the resistance, the more of the applied voltage it will capture, and the ratio of the voltages across series resistors will be the same as the ratio of their resistance levels. As you can see in this simple circuit, the largest resistor captures the bulk of the applied voltage, while the smallest resistor has the least. And the ratios of R3 and R1 are 6 times larger in both resistance and voltages. To find the voltage and resistance of each, you'll first need to calculate total current, and then use Ohm's law to calculate the voltage over each resistor. However, this can be calculated by the voltage divider rule, which permits the determination of the voltage across a series resistor without finding current of the circuit. First, we will determine the rule. Using total resistance and the fact that the currents are equal, we find that V1 and V2 equal this. Therefore, Vx equals Rx E over RT, where Vx is the voltage across the resistor Rx, E is the impressed voltage across the series elements, and RT is the total resistance of the series circuit. Therefore, the voltage divider rule states that the voltage across a resistor in a series circuit is equal to the value of that resistor times the total applied voltage divided by that total resistance of the series configuration. This rule can also be used for series circuits with any number of series resistors. Now, an example of this is this circuit, where RT can be calculated to be 15 kiloohms. Using this and the source voltage, we calculate that V1 equals 6 volts and V3 equals 24 volts. The voltage divider rule can also be extended to the voltage across 2 or more series elements. For example, if we combine V1 and V2 in this case, we end up with V' be equaling 21 volts, as you can see by the calculations. So now we know how to calculate series resistant voltages in DC, but what if we have an AC voltage applied? Well, we can use the same rule, but we need to have all the values in polar form and calculate using polar and rectangular form, so that we have a voltage and a phase angle. In this example, we can sub the values into the same rule and use polar and rectangular form to end up with 30 volts with a phase angle of 83.13 degrees for VR, and VC equaling 85 volts with a phase angle of minus 6.87 degrees. Well, that's all for today, and hope you all now have an awesome understanding of voltage division.